In the name of God, the compassionate, the merciful, engineering plasticity, Chapter 5, Elastic Plastic Analysis of Bending, Part 4. In this part, we are going to talk about plastic bending analysis, but this time about a spring back. Let me just explain what we mean by a spring back. It means that when we deform a piece of material, it will spring back a bit towards its original position. Now, the simplest thing is this beam. That's the beam we are considering. Okay, there's a cantilever beam in here, and we have this force acting at the end of the cantilever. When we apply this force, we get a deflection delta. Okay, if this delta, the deformation, is completely elastic, that means that we increase F up until before we reach the yield point. If this F is smaller than the force required for the material to yield, it will be in the elastic range. Therefore, delta will go back to zero as soon as we release the load. Okay, if we take off the load, it will go back to its original position, which is here. No plastic deformation. But if we increase F greater than the yield point, okay, increase F so that the bending moment stress which is applied here is greater than the yield stress or yield strength, then it will deform plastically. It depends how much we increase F over the yield point. And what happens is that when you release the load, if you take off the load from the beam, then the part that has been deformed plastically will remain permanently and will not change. But the part that has been deformed elastically, which is this part, will go back to its original place. So this beam will go back a little bit, but this is the permanent deformation delta F, which remains and does not change. And we call that a spring back because it springs back to its original place. You know what a spring is and what it means. So that's a spring back, and it doesn't only happen for beams. You know, it happens for plates as well. Especially, you know, in our industry, we have a lot of forming on sheet metals. Here I have shown an industrial process called air bending process. You can see the die here. We have a die, we have a punch, and we have a sheet of material which is originally a flat sheet of material lying on this die. The punch comes down and pushes the sheet metal and forms it like that. Okay, it forms it like this. When the punch is removed, the unloaded part becomes like that. You can see that the original radius is much sharper than the final radius. It's like here, you know, it's come to here, it's come back there. So this is the loaded part. When we have removed the punch, it has sprung back to original position. So we call this a spring back. You know, the difference between these two angles, or between these two radius of curvatures, between the two curvatures. Now, in order to calculate or compute this spring back, which is a very difficult problem when you have sheet metal forming, we could assume a plane stress condition. What does plane stress means? It means that we have a stress only in one plane. Okay, all the stresses are in one plane. We don't have any stresses perpendicular or having an angle to a plane. Just all of them in one plane. If that is so, we could assume a plane stress, then we could use this solution that I'm going to show you here. Now, of course, what I'm going to show you is a very simple solution for pure bending. But in industry, we have molds and dies and tools which exert many stresses from different directions on the sheet metal and deform the sheet metal. And it's a very complicated situation, therefore we could hardly use these simple computations. It's just to show you here that how we can compute the spring back, but of course we could use finite element simulations as well. Here we have a beam here, and that's the cross section of the beam, and as we have said here, H and B, H is the height of the beam and B is the width of the beam. That's the cross section, and these values, dimensions of H and B are comparable. It means that they are near to each other. If B is very much greater than H, then you cannot assume a plane stress for this condition. But here we could assume a plane stress condition. Okay? Now, it says that then it could be assumed that there is no significant stress in the plane perpendicular to the bending plane. Bending plane, of course, is along the XY axis. Okay, XY plane is the bending plane because we are bending like that. So it says that we could assume there is no stresses in the direction of Z. Okay, so that's of course there are some stresses in the direction of Z, but because they are negligible as compared with the stresses in the XY plane, we say there is no stress or significant stress. So that's why we say plane. So it's in the plane of XY. And we had these relationships from previous parts. Yeah, elastic strain is equal to Y over E or Y over R. That Y was the distance of the fiber that we were considering the elastic strain for it, and that R was the radius of curvature of the fiber, which is the neutral axis, and that Y is the yield stress, and that's the modulus of elasticity. Now, MEP, that expression we obtained before. MEP is equal to YB over 12, 3H squared minus 4Y squared. Of course, here again, we have a rectangular section, and we obtain this for the rectangular section. But if the section is changed, for instance, circular or anything else, then this will be different. Now, we substitute from this equality Y equal R times Y over E. So that Y is omitted, and we have MEP here equal to that. Okay, B, Y, H, E, and R are all known. Okay, therefore MEP is known. That is, for the elastic plastic case, on the boundary of the elastic plastic boundary. Now, the radius of curvature after unloading is determined by the following method. We want to determine the radius of curvature after unloading. So that's the radius of curvature when it is loaded, fully loaded. Then if we take off the load, the beam goes back to here, not to its original place, because there are some plastic deformation. So the radius of curvature of this beam, if we want to calculate that, okay? So, because if we could calculate that, that is, and we also have the curvature of that, then the difference, which is delta E, is the spring back, okay? Now, this is the relationship we have for the elastic plastic boundary, okay? Since here we have also elastic plastic boundary, because part of the beam is plastic, part of it is elastic. So on the elastic plastic boundary, that is the relationship, okay? If it wasn't on the boundary, it was on the plastic part, then we would get another relationship. If it was in the elastic part, we would get another relationship. So this is in fact MEP for the elastic plastic boundary. Now this is what we mean, which happens in the cross-sectional area. In fact, from the outermost fiber to some place in here, which is called Y' in this figure, all the area is plastic. So that's the plastic, and that's the elastic. That's plastic. So the boundary of elastic plastic is this. So this MEP is the force applied and increased so that MEP reaches a value such that the plastic region progresses up to this point. So this MEP is for this boundary. That is the elastic plastic boundary. And M, which is for the elastic case, that's for the elastic, okay? Since you know that whatever the material is and the loading is, when you unload, unloading happens elastically. Plastic unloading does not mean anything because it doesn't happen. You know, when you release the load, if the material goes back to some position, not to its original position, to some position, that movement from the final position to the middle position, like here, from here to there, that happens elastically, because plastic deformation is permanent, it doesn't go back. Only the elastic deformation goes back. That's why we have written this here. So EI over RE, that is the RE for this curve here, okay? And we could write here EBHQ over 12 for BHQ over 12 is for I. Substitute for I for the rectangular case, and then we have EBH cube 12 RE is equal to that. Why we put it equal to that? Because this is on the elastic plastic boundary, and this is the moment that we are taking off. While taking the load off, we are taking this moment off. Therefore, we put this equal to that. You see, when we apply the load F and increase it up to this point, we get the moment MEP equal to that. Okay, then we stop the loading and unload. When we unload, the moment is equal to that because it's elastic. Okay, so we have applied F, we have taken off F. So the effect of F must be taken off. F has caused some plastic permanent deformation like that, and some elastic deformation like that. When we take it off, we must take all of F off the beam. Okay? So when we want to calculate the unloading of the force, we must use the unloading of the moment and the elastic moment. And so that's why we put these two equal to each other, because we have applied F. Now we have taken off F. So F is equal to 0. So we must take the effect of F off the beam. And the effect of F is the elastic moment. And that's why we put these two equal. And from there, we could get RE, because RE is the radius of curvature for that. And so you have to do some manipulations here, put this equal to that, and then 1 over RE, bring all of these terms over here and do some simplifications, and therefore you get 1 over RE is equal to 3y over EH minus 4y cube R squared E cube H cube. And then here we use some simple geometry. We say that if this L is this beam, okay, straight, that's the beam, that's L from here to there. And when it deforms like that, that is the beam deformed. If we continue this curve, and supposing that this is a part of a circle, this deformed beam, then we could have a big circle like this with this geometry. What is this geometry? As you can see, the curvature of this is R, because we said that the curvature of any deformed beam, we could consider it as R. So that's the curvature. And if we the diameter will be 2r, and if we draw this line here perpendicular to 2r, then we get that bit is delta, which is the total deformation here, from here to there, like that, from here to there. That's the deformation, total deformation. So that line gives us angle alpha, and since that is L, so that should be L as well, and that is alpha as well for the geometry of the circle. We know that this is true, since tangent alpha is delta over L. Okay, this tangent alpha is delta over L. And also for the big one here, big triangle, tangent alpha is equal to that L over this part, which is 2r minus delta. And then equating these two, we get L squared equal to 2r delta minus delta squared. And we could approximate this as delta times 2r almost equal to L squared, because delta is very small, so delta squared is very small. So we can put it equal to 0 and put this equal to that, and then delta is almost L squared over 2r. It means that this equality means that delta is inversely proportional to radius of the curvature, and therefore we know here that delta F, which is the final deflection, is equal to delta minus delta E. Okay, so since delta is proportional to the inverse of R, therefore we could write here 1 over RF, 1 over R, 1 over RE. What is this L? Delta E is this bit, which has gone back. That's the spring back. And therefore R over RF is equal to 1 minus R over RE, and we have already obtained 1 over RE here. Okay, therefore we could substitute here, and then we have this relationship, R over RF equal to that, and finally if we rearrange this, R over RF is equal to y r over EH plus 1, 2y r over EH minus 1 to the power of 2, and everything is known here. Also R is known, okay, because R is this radius of curvature of the final position here. So we know the final position, so we know the R, okay, and we can obtain R. And therefore RF can be found from here, okay. In this equation, R is the radius of curvature in here. RF is the radius of curvature of the final position, okay, that's the final position, delta F, RF. So if I put here RF, I get delta F, okay, that's the spring back. And from this relationship, we could see that if R over RF is 0, then the bending is completely elastic and the spring back is complete. It means that it goes back to its original place, okay. The spring back is complete. It means that we have no plastic deformation, no intermediate position. So R over RF becomes 0. And if R over RF is equal to 1, then there would be no spring back. Okay, it won't go back at all. In fact, this delta E vanishes. It doesn't go back. Delta E is 0. So if we deform it to this position, if R over RF is equal to 1, then it means that we don't have any spring back. Complete plastic deformation.